A user updates a product price to $10. The database saves it, but the cache still serves $5. The customer pays $5 and your company loses money immediately. Computer science has two hard problems: naming things, off by one errors, and cache invalidation. Invalidation is the process of declaring cache data as no longer valid or accurate. In high-performance systems, reads hit the memory-based cache, while writes target the persistent disk. This structural asymmetry creates a race between the speed of memory and the durability of disk. The most common strategy is time to live. Every entry gets an expiration timestamp. Once the clock hits that limit, the cache discards the value, forcing a fresh fetch from source. Time to live introduces a predictable staleness window. If your time to live is 60 seconds, your system might serve incorrect data for up to 1 full minute after a database update. Write-through caching updates the cache and the database simultaneously. The application waits for both to confirm success before acknowledging the operation to the user, ensuring immediate data consistency.
While write-through provides strong consistency, it increases write latency. Every write must wait for the slowest component, usually the disk-based database, negating some of the speed benefits of caching. Write-around caching sends data directly to the database, skipping the cache entirely. This prevents the cache from being flooded with data that might not be read again for a long time. In a write-around setup, the first read after an update results in a cache miss. The system must then fetch the data from the database and populate the cache for future reads. Write-back caching acknowledges the write as soon as the data reaches the cache. The update to the permanent database happens asynchronously in the background, offering the lowest possible write latency. The danger of write-back is data loss. If the cache server crashes before the background process persists the data to the database, that specific update is gone forever. The cache aside pattern puts the application in charge. The app checks the cache first. On a miss, it queries the database and manually updates the cache with the retrieved result.
When using cache aside for updates, you should delete the cached entry rather than updating it. Deletion is idempotent and avoids race conditions where two concurrent updates could leave the cache inconsistent. Purging simply removes the data, while refreshing fetches the new value immediately. Purging is safer, but causes a latency spike for the next requester, who must wait for a database fetch. Advanced systems use change data capture. The database transaction log is monitored. Any committed change triggers a background service that invalidates or updates the corresponding keys in the cache layer. Many large-scale architectures accept eventual consistency. This means there is a brief, measurable delay between a database write and the cache update, during which the system is technically inconsistent. When a very popular cache key expires, thousands of concurrent requests might hit the database simultaneously. This thundering herd can crash your backend before the cache has a chance to refill. To stop the thundering herd, use request coalescing or locks. The first request to find a miss acquires a lock. All other requests for that same key wait for the first to finish.
Instead of waiting for expiration, probabilistic early recomputation refreshes the cache before it dies. It uses a random variable to decide whether to refresh as the time to live nears its end. Tagging allows you to group related cache entries. When an underlying object changes, you invalidate the entire tag. This clears all related views, fragments, and queries in a single operation. Versioning turns invalidation into a naming problem. By including a version number in the cache key, you never update data. You simply write to a new key, leaving the old one to expire. The lease pattern grants a client a temporary right to update the cache. This prevents stale values from being written back by slow, lagging processes that have been superseded by newer updates. Negative caching stores the absence of data. If a user queries a non-existent ID, you cache that null result. This prevents attackers from bypassing the cache to flood your database with misses. To avoid massive simultaneous expirations, add jitter to your time to live. Instead of exactly 60 minutes, use 60 minutes plus or minus a random number of seconds to spread the load.
Updating a database and cache sequentially is not atomic. If the second operation fails, your system enters an inconsistent state. Distributed transactions, or two-phase commit, are often too slow for this. The Outbox pattern ensures atomicity. You write the update and an invalidation message into the database in one transaction. A separate relay then picks up the message and clears the cache reliably. In a distributed cluster, one node's cache update must reach all others. Use a publish-subscribe bus to broadcast invalidation signals. This ensures that memory caches across all web servers stay synchronized. Caches often exist at multiple levels, from the browser to the content delivery network to the internal service. Invalidating the source requires a coordinated flush across the entire delivery chain to be effective. Content delivery network invalidation is rarely instantaneous. Global propagation can take several seconds or minutes. Design your application to handle this delay by using versioned asset URLs for static content changes. Some systems use logical inclusion. A parent object includes a last modified timestamp. If the parent timestamp is newer than the cached child object, the child is implicitly considered stale and ignored.
During high traffic spikes, defer intensive invalidation tasks. Queue them up and process them when the system reaches a quiescent state. This prioritizes immediate availability over perfect consistency during peak stress. After a massive invalidation, the cache is cold. Proactively warm the cache by prefetching the most popular items. This prevents the initial wave of users from experiencing slow, uncached response times. To prevent cache-wide contention, use lock stripping. Instead of one global lock for invalidation, use multiple locks based on the hash of the key. This allows parallel updates for different data segments. In microservices, one service's cache depends on another's data. Chain your invalidations through event headers. This creates a reactive pipeline where downstream caches automatically flush when upstream sources announce a change. Quantitative analysis helps set invalidation frequency. Determine the maximum allowable age for every data type. High-precision financial data requires immediate invalidation, while social media likes might tolerate several minutes. Leverage standard structured query language or hypertext transfer protocol headers like ETAC or if modified since. These allow the server to tell the client the data is unchanged, saving bandwidth.
Use a consensus service like Zookeeper or etcd to manage cache state across clusters. These tools provide a consistent view of which version of a resource is currently valid globally, eliminating local drift. Some caches support a stale while revalidate mode. It serves the old value immediately while simultaneously triggering a background update. This keeps the user experience fast even when the data needs refreshing. Complex invalidations require a dependency graph. If you update an author's name, you must invalidate the author profile, all their articles, and the search index entries. Track these relationships to ensure completeness. Invalidation based on unique keys is easy, but range queries are difficult. If you add a new user to a department, you must invalidate all cached lists of users for that specific department ID. Use Bloom filters to quickly check if a key might be in the cache. This saves unnecessary invalidation commands for keys that were never cached in the first place, reducing network overhead in clusters. Logical replication provides a high-level stream of data changes. Unlike physical replication, it describes changes in terms of table rows, making it the perfect source for precise per-key cache invalidation logic.
Monitor your cache hit ratio and your invalidation rate. A high hit ratio is good, but if your invalidation rate is too high, your cache might not be providing any actual performance benefit. Test your invalidation logic under high concurrency. Use tools to simulate network delays between the database and cache. Ensure that no sequence of events leads to a permanently stale cache entry. There is no single perfect strategy. For consistency, use write-through or outbox patterns. For absolute speed, use write-back. For simple implementation, use cache aside with a sensible time to live.